Welcome to a new test and teardown video. This time it's going to be a follow-up. I already released a video about the RE Radiometer Electronics 4-channel universal power sync. As you see here, it's about 3 months ago. And I will, of course, put a link to the original video. And this is, of course, where you need to go to understand all the basics and all that kind of stuff. So the reason why I'm making a little follow-up video about this power load here, that is because now 2 of them are not working and I need this load. I was actually using this load at work at a customer site because I needed more loads, and we don't have enough of the more modern loads that looks a little bit like this. This is of course what you buy when you need a new modern load, but when you need a lot more individual channels, why not pick up some of your oldies and use them along with all the new stuff, so you have enough channels. So the story is number 1 and number 4, they are not working anymore. They are shorted. So I'm going to figure out exactly how this works. How can I repair this? And should I just replace it and fix it as it is and don't modify, improve or anything like that? Because this load is not a constant current load. It's not a constant resistance load either. It's something in between. So you just adjust to whatever kind of load and stuff you want, and then when you change the input DC voltage, you will get a change in current. But it's not exactly either constant current or constant resistance. I mean, it's somewhere in between. So, but it's perfectly useful just to load stuff. You know, if the voltage change, okay, fine, you just fine tune. It's not a big deal really. But I wanted to see how is this really made. First, let's dig into the transistor. So this is the power transistors. We got 4 power transistors per load channel, and those are BDV67B. So that means it's about 100 volts, about 100 and something watts. The old data sheets, they say 200 watts at 25 Celsius. Yep, and the new data sheet says 125 watts per device. And they can also handle 16 amps maximum. It's a Darlington transistor with very, very high DC current gains. So it's between 1,000 and 3,000 depending on the DC current. So that is a huge advantage in a system like this. So you only need tiny little transistors like we see here to actually control those big power transistors. So all that is perfectly fine. Did I also mention that this type of power sync, they don't use any external DC supply or anything like that. So each board is simply powered by the DC voltage that you apply to your load. So it lives off this as well. So that is quite smart. So this will give you a nice individual approach where you can parallel them or whatever you want to do with them. Also, each of the loads, they go to 4 sets of transistors like this. And then there is again isolation. See, each of the heat sinks, I don't know if this is real visible, but there is some sort of a plastic type around here, and everything is isolated. So that will give you a very, very high isolation voltage between the channels, but it will also give you a very bad thermal performance. So if you don't need this huge isolation voltage, I would have designed it so the 4 transistors for each channel would have been like 1, 2, 3, and 4 on the heat sinks like that. Because then, when you don't need it for a full power capability, you could probably, not use the fan, because you will now have a much better distribution of your temperature, because the way that you do it here, you just heat up one of the heat sinks like that. And I mean, this is of course not as smart. You want more metal, right? Also, how about the way that they have mounted each circuit board? This is definitely not a way to create high isolation. So this is, again, they didn't get any high isolation, because you can see this is the circuit board mounting hole. That will be metal, right? And again here, see? Metal all the way around that hole. And down here is a hole that is even smaller. See the distance here, some tracks to the mounting holes. And then if you compare the brass standoffs, they even had to, see, mill this one in the top. And I think the other standoffs here, they are more or less almost touching. So this load is not having a huge DC voltage isolation potential between the 4 channels. So this is something I should definitely be aware of. Also, those connectors here and everything, they actually do handle thousands of volts. Not officially, but they actually do. Potentiometers here. That is something I would be very afraid of, especially this type, because the distance from metal to the different parts in there is very small. The Elmer switch is very good for high voltage, because everything is high up, far away, and the way that they are made is actually quite good for this. So yeah, and this one is also acceptable. These switches are normally used for mains and such, so they're also quite alright. So yeah, I think what I want to do is try and make you a nice schematic of this circuit board and try and explain exactly how it works, because then we should be able to figure out how to repair it. So we need to figure out the wires for the potentiometer. So this is the fine adjustable, and this is like ranges where you select the range where you want to be, and then you have a fine on the potentiometer. Those 4 wires, they go to that connector, and they even coded the connector so you can't put it in wrong, I guess. See? So that's smart, and it's numbered. So far so good. All I have to do is unmount all the different, and here we need to desolder something. That I think that will be the 2 wires that goes to the amp meter, and then there is a little amp meter switch for 5 amp or 20 amp full scale, and then you push the switch, and then you have to hold it into the 5 amp range, and then you let go, and then you're now in 20 amp mode. And all that they do is measure the voltage drop over one of the current sharing resistors for each of the 4 power transistors. I would have taken resistors from each of those 4 and added like an add point, and then measured the sum of the currents in all 4, and that is what I would have displayed on the meter. That will give me a much more accurate representation of the total current. Also, what we see here is 0.1 ohms, so there's hardly enough feedback to share the current between the 4 transistors, because we got a little PNP transistor here, and I think this is used to measure the voltage drop and then regulate a current sharing between the 4 power transistors. Now, there is actually one thing I really like with this design here. You see the, of course, the red and the black wires. They're of course the same color for all of them, and then there's a thin one. This is the base signal, and that's different colors. So now you can follow the wires here onto the heatsink, and then you'll know these 3 goes to this transistor and so on. So that's a quite smart way to do it. But why would you have these thick, insanely crazy thick wires? Because we're only doing 5 amp per transistor and we want to dissipate power, I mean, it is perfectly fine to lose some millivolts and some watts. I mean, it's perfectly all right. It's only an advantage to run with a little bit, small heat added to your wires. That's perfectly fine. And these super thick wires, they just drive you nuts when you are making stuff like that. It's just not needed. Yeah, and that is the disable op amp and the control signal to a BNC connector. That is just for enable, or yeah, of course for disable. It is by default enabled. So if you activate the op amp, you will disable the load for remote test application and such. So that's quite all right. I've been, as I said, using this load the whole week, and what I can tell you is that channel 2 and 3 works perfectly fine. And I do see a lot of drift in the set point. So if I have 12 volts and I set it for 4 amps, then I need to go during the first few hours and fine tune it, and then it will stay quite all right near the 4 amps when everything is warm and nice and stable. But it's this unstable behavior the first few hours, that is something I would like to see improved if I should use this a lot more in the future. I think I did promise you a schematic of this fantastic circuit board. First, I think we should look a little bit here and see what I've done. First, I wrote down all the different connections to the potentiometer, the switch, and then I numbered the transistors so I know where we are, what we're doing, and then I just traced down the schematic. It's quite simple because all these 4 parts here, that's exactly the same, and everything just repeats. And yeah, then we got a few two little transistors here, and an optocoupler, and a trimmer around the optocoupler. So, of course, you just write down the pinout of your transistors, all of them. Well, that's the same as this one. And then first I did a little fast hand drawing like this. It's not really nice or beautiful. And then I redrawn everything here on my computer, so it's really nice and beautiful. And this I can use to explain you how it really works. So, if we look at the switch, that is the key to all of this really. That is to understand the feedback. Where is the DC stable feedback really? And I only drawn the first 6 position. It's really a 12 position switch, but you can of course use your imagination and figure out that we will just continue all the way this way. Minimum goes all the way to short here. So the idea is, if we have a very, very low resistor here, right? So this emitter is connected to the center point of all these resistors. Those are of course the individual sense resistors to the 4 power transistors. And the more current you pull through one of the power transistors, the more voltage you will have over this sense resistor. That's quite obvious, right? So if this voltage here is higher, that means this point will be lower. Okay? Then it will turn this a little bit more off, right? By pulling this down. And then you will have a stable system because all these, they go together to this point here. And that point here is again fixed via this base emitter. So that is actually how it is handled and how you have the current share. The problem with this system here is you have this base emitter here and you have this base emitter here, and this is your current feedback loop, as you can imagine, right? The stable system here, right? So what I've drawn here is the temperature problem. So if you heat up this transistor, your current will go down. If you heat up this one, your current will go down a lot. This one is crazy temperature sensitive. If you heat up this one, your current will get up. It's not as crazy sensitive as this one because you have 4 of them, right? So you only, yeah, that is of course how it is. If you only had one of these, it will be exactly the same temperature dependency on your current as this one. So if we look at the board again, we will see that Q8 and Q9, they're actually mounted really close to each other. So I think the designer of this board did it right. His intention was that you're supposed to glue these two together to have as little temperature dependency as possible. However, the guys who implemented this into the real world, they forgot about this, didn't read that memo, so they just put the 2 transistors like that. In some of the other units I got, they're actually bent away from each other or something like that. So this is definitely what I want to fix when I repair this unit here, and see if it is a lot more stable, because it really drove me a little bit nuts that I was going to readjust all the time. The optocoupler system here is also not super perfect. The whole idea about it is you can put in a signal generator or a remote turn off signal, activate the optocoupler. The optocoupler will pull a signal into that Q10. So when this signal pulls up, you can imagine that it will now turn off this transistor. And by turning this transistor off, you're going to lower the total current. However, the idea is with this trimmer here, you can adjust how aggressive do you want this to be, and it is really not that much. It is only quite good in the very low current settings, but the higher and higher your current setting will be, then this becomes less and less effective, or almost has no, I actually don't do anything. So what I want to see, if I could probably remove this and put this signal somewhere else. Probably I can put it all the way here and turn this transistor completely off by activating that one. That will make me, so I can turn it completely off. I mean, I want to, if I really want this, I want it to be a 100% on-off kind of thing. So that is, that will be my first modification to do. And then I will, of course, thermally couple these two, and then I will have a nice working system. Also, I found the problem with this channel, and it's just a shorted transistor. One of the power transistors was just shorted. So by opening one of these transistors, I have, of course, a system that is working, but now it can only do 2/3 to 3/4 of the total current and total power. But I will just put in a new transistor, and then it will be good to go again. I should probably demonstrate the thermal effects of the transistors. So look at the amp meters. That is the lowest bottom there. So it's 1.78 something, right? And then I believe this one here is number 3 that I'm playing around with. Okay, so here is the Q9 is that one, okay? I'll just barely touch it with my solder iron, and then we'll look at what's gonna go and happen at the same time. So here, 178, and then just touch it. See? Current goes down, okay? Then we wait a little bit, and then it's gonna go back up again, okay? Then I'm gonna go and touch Q8. That is the one up there, okay? It's still not going, it's not gonna go all the way up stable again, but let's just try and touch the other one and see what happens. See, current goes up. Exactly as I said. and they are mounted very, very close. So what I did in my other board that I'm playing around with, see, I bent them a little bit closer like that by pushing them and soldering and all that kind of stuff. And also what I did, so this is the optocoupler here, I removed these two and connected that signal to Q9. So I believe when I turn this off, when I turn on the optocoupler, I will turn off this transistor here, and that should remove the drive. I hope. We will see what happens. I want to share with you what I've been yelling and screaming about for the last half an hour. Oh, how stupid. I want to change the field, the transistors, right? See, this one was shorted, and I proved that by lifting the wires. So of course I want to replace the transistors and all that. But to get access to the transistors, there's no way I can get in here, right? So I need to lift these out, and these are individual little units. But as you can see here, they are interlocked with these pieces here. So you need to get these out, right? You see the screws here? This screw is somehow locked, glued, or some other trick in there, so it's not going out. Then it's isolated along the heatsink, and then there is a nut on the other side. If it could have been so easy if only this was a very long screw. So you just take out the entire screw, and then you can pull out the entire heatsink and do your service, and then just slide it in. Oh yeah, but that is not how it is, right? So you need to remove these brackets here because you can't pull the screw out. And that is of course impossible because the brackets, they are screwed here. And when you unscrew this screw's gonna turn around. So I managed to get them out in one end here, and then hopefully I should be able to get everything out here with all my long screws. And I mean, if I don't break anything, cause a lot more problems, you will see this is probably just the most unservice friendly construction ever. And you see, they're interlocked. But why? Why would you do that? This is of course because you want the air to go that way. But couldn't it have been made in such a way so it's airtight but not interlocked? So, I'm absolutely angry about this. The level of stupidity just have no limit in this one. So when you pull these out, because you want to pull out the heatsink, right? I don't know if you can see this, but there's a little groove that goes into the ends here, right? And obviously these four little ends, they are of course loose individual items. So when I pull this out, of course they're gonna fall out in the other end, and they're going to be real funny to put back here. I mean, how the heck is this going to be possible? I'm gonna blow all my last fuses on this one. If somebody with a little bit of brains could have glued these to this piece, I mean, that could have been done, right? I did it. I'm happy again. I got it out. But it's really, really stupid to use so thick wires. I think now I got this out anyway, and I need to rewire everything here and make this nice and fine. I really want to use super thin wires, because you really don't need thick wires. This is only 5 amps per unit. You could use thin wires. It's absolutely stupid. But this one is defect, and these 3 works. So my idea is, because I got 3 of the loads, right? I want to take the other transistor from the other one that is not working, and put it in here. So I got all these. But First of all, I replace all these with new ones, and then I can save these 3 to repair the others, the other one. That is at least my idea. Let's get one up and running. That is real good. So here is this section with 4 new transistors and a little bit thinner wires. I mean, compare my wires to the original wires. I think it's gonna be fine. So now I'll try and assemble this section and test my little modifications and see if it's more temperature stable. So this is my first test with the new transistors before I assemble everything. Of course I want to test, it's just flying all over the place here. Well, now I can easily put in my circuit board and do the rest of the things. So I think I kind of nailed it. Yeah, I solder everything on here. I don't want any loose connections or anything like that. So what I wanted to show you is the way that the transistors, the power is equally shared between the transistors. This is super easy to reveal with a thermal camera. And at this kind of super low current, I don't really see any kind of temperature rise on any of the resistors right here, because the voltage difference between these, it's like really, really low. Remember, it's designed for 20 amps and it's 0.1 ohms. So yeah, that drop is really low. I can also show you that this is of course not a constant current load or anything like that. It is just a variable load. That is the main purpose of this thing. So that means if I give it, this is the lowest possible setting, all right? So at the lowest setting, yeah, it is 1.2 amps at 12 volt, but if I crank down the voltage to 5 volt, you see, it is a lot less. And if we stay here at 5 volt, and now I crank up my load, clickety, 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 now my range setting is at maximum, and then I crank up my potentiometer. You can see we can go all the way. Ooh, and that is the limit of this tiny little power supply here. If I continue to smash it up, see, it goes down to 1.8 volt. And so I think I'll be able to, yeah, you can parallel these and all that kind of stuff. So I think this will give me a nice range for whatever I need. Normally, I don't need to load a lot of current at 5 volt. And this is certainly not this load. It's not for that. But I could, of course, also make a real constant current load with field effect transistors, a little op amp, a really nice voltage reference, and all that kind of stuff. So I was actually able to get this circuit up and running using my new NPN Darlington transistors and all that. This is paint for my thermal camera. I'm doing a little bit of investigations and experiments to figure out what kind of thermal conductivity I got here and all that kind of stuff. So this is just a little bit of side research. Why not take advantage of this test setup and do a little bit of research anyway? How about trying a little modern approach? I don't know if you can see what I've done here. Oh, this is like a 10 minutes, let's hammer the whole thing together as fast as possible. But you know what? This circuit here works a lot better. It is so stable and absolutely fantastic. And maybe I should show you what I have done here. So this is a 1K multi-turn potentiometer. I got a little 1.2 volt reference down here. Yeah. In the beginning, I was just using a normal diode because I need only a half a volt full scale on my potentiometer. But now I use a 1.2 volt reference, and here is another K, and then it's going from 0 to 0.6. So that voltage is here. This is my wanted voltage that goes to my op amp. Okay? Then I got a sense voltage from one of the 4 emitter resistors. Again, I'm using 0.1 ohm just to be super fair, so everything is exactly like it used to be. But I've put in my resistors in the emitters of all the 4 transistors and all the 4 collectors. That is my positive input, as you can see here, right? And then I got a little resistor here from that sense point to the input of the op amp and the output of the op amp. I got, of course, 4 resistors, so I can control the 4 base input to the 4 NPN transistors. And this is my integrator capacitor. So of course you need an integrator. This way you get 0 fault and you can have maximum gain at 0 hertz. This is a fundamental way of doing a constant current regulator. So my power supply here, I just had a 100 nano decoupling, and then a 10 ohm resistor, that is that one, and a local decoupling for my op amp. Yeah, and here is a resistor from the positive to my voltage reference. Now let's try something funny and just crank on the voltage. And what you see here is 3 amps. It goes plus minus a few milliamps per little micro click when you poke around with the multi-turn, because it's 0 to 20 something amps. So every little micro turn here is a few milliamps. And then you see here it is very, very stable. If I take, this is voltage. Let's just crank it up. 1 more, 1 more, 2 more, 3 more. So you see it's quite stable. The little extra milliamps you see here, that is actually because the resistor to my voltage reference, of course, uses more and more current. So that is actually the current into my Zener reference. And of course, more current into my Zener reference also raise the voltage a tiny little bit. And that means my set point is, of course, also pulled up a little bit. So I think I will try and clean this circuit up, and I will make it nice and shiny and put it in there instead. And maybe I will do this with all 4 of them, but at least this is what I want to do with one of them. Just to show you a little better here what I've done. So it is nicely hand drawn like that. Of course, you got 4 of these in parallel, you got 4 of these in parallel, you got 4 of these in parallel, and 4 of the transistors. All those are 4 of them in parallel, right? And they all connect to that point, and they all connect to that point. The reason why I want 4 of these resistors here is because I want to use all the 4 individual emitter resistors, and I want the average to be my feedback. This is a little bit more stable way to do it, and this is also the point where I want to use my amp meter on all 4 of them. This is just a little way to do it a little bit nicer. And yeah, here's the integrator, super important. Because there is a tiny little bit of offset voltage in the op amp, what you want to do is you want to raise the feedback voltage a tiny little bit, just at least the millivolts you can have of offset. And that means you will now be able to go to 0. Isn't that smart? Otherwise, you will only go down to whatever your offset is. So just a little, I have a 47K here. So it's just a tiny little bit. And here is my 1.2 volt reference. It's an ICL 8069. Those are really nice and fine. And you need a little local decoupling for that. You also need a local decoupling for your op amp. And here is what I want to add, because I want to be able to use this at 5 volt and 60 volts, stuff like that. So of course I need a series regulator for my op amp, and I want this voltage here to be quite low and more or less sort of stable, so that I have the same kind of voltage into this system here. So it's going to be really nice and fine. By the way, if you want to add a disable, like a disable switch or a disable input, what you do is you raise this voltage. This is what you pull up by your op amp or something like that. You pull this up. You don't pull this down. This is not good. So it's always a good idea to pull this up, and then it will still be into regulation and all that. So this is a much better way to do it. And that is what I wanted to show you of my little constant. It will now be a constant current power load. Thank you very much for watching. Bye bye.